Welcome to the Deep Dive, your shortcut to being genuinely well-informed. We cut through the noise, uncover the fascinating stuff from the latest research.
Great to be here.
Today we're diving deep into, well, one of the really big challenges for AI right now. How do you make sense of truly vast amounts of information?
Yeah, not just quickly, but deeply.
Exactly. Think about an AI trying to grasp an entire library, not just one book or maybe not even a full chapter.
It's this ongoing quest, and it really hits a critical bottleneck with the models we have today.
Totally. On one side, you've got the giants like Transformers, incredible architectures.
Oh yeah, amazing at understanding context, connecting ideas across, huge stretches of text, page 1 to page 500 kind of thing.
But there's always a but. That power comes at a serious cost. The computation required just explodes.
Quadratically, that's the key term.
Right. So if you double the information, you don't just double the processing time.
Nope, you quadruple it.
Ah.
Or worse, it gets really, really expensive, fast.
It's like having this brilliant researcher, but their reading speed just tanks exponentially the more pages you give them.
That's a good analogy. Then on the flip side,
You've got the more efficient models, like these modern RNNs, recurrent neural networks. Mamba is a big one here.
right, Mamba, designed for speed, they scale linearly.
Which sounds great. Double the data, double the time, much more manageable.
Absolutely. But here's the catch.
There's always a catch.
Their ability to genuinely use that really long context to pull out new insights from this ever-growing stream, it still hits a wall.
I can't quite hold on to everything, especially the subtle stuff over vast distances.
Exactly. They struggle with that deep, long-range dependency.
So this is the tension, right?
Yeah.
Deep understanding versus efficient processing, especially when you're talking tens of thousands, maybe millions of tokens.
It's the fundamental trade-off.
Okay, so today we are taking a deep dive into a really groundbreaking paper. Comes from a powerhouse team, Stanford, UC San Diego, UC Berkeley, and Meta AI.
Quite the lineup.
It's titled Learning to Learn at Test Time, RNNs with Expressive Hidden States.
Catchy. The parenthetical's doing some heavy lifting there.
It is. Our mission here is to unpack how their new approach, test time training or TTT, how this could be the key.
The key to AI that can handle massive info streams without getting totally bogged down.
Exactly. It feels like a really pivotal step in how AI learns. Okay, let's unpack this.
Let's do it.
So here's where it gets really interesting. This fundamental trade-off, fast versus smart with long info streams. Researchers have grappled with this for years.
Oh, absolutely. Imagine processing, every book ever written chronologically.
Wow.
How do you keep integrating that new knowledge without the system just collapsing computationally?
Or just forgetting what happened way back at the beginning.
Precisely. That's the core problem TTT tries to address. That tension, it drives so much innovation.
And when we talk linear versus quadratic complexity, maybe break that down a bit more.
Sure. So linear is predictable, right? Processing time grows directly with the amount of data. Nice and steady.
Manageable.
Quadratic, though, that scales much, much faster. It quickly becomes, well, frankly, unmanageable for really large inputs.
Like the transformer trying to pan its powerful microscope across that vast landscape takes forever.
Yeah, exactly. Well, the traditional RNNs are more like a fast scanner, but they miss some of the deep detail as they go.
And the paper really calls out this awkward reality, as they put it, for even modern RNNs like Mamba.
Right. Mamba's made huge strides. It performs really well, similar to Transformers in overall prediction accuracy, this perplexity at, say, 8,000 tokens.
Okay, so up to a point, it keeps pace.
Up to a point. But when the context gets really long...
That's where it struggles. And maybe explain perplexity quickly.
Right. So perplexity is basically a measure of how surprised a language model is by the next word it sees.
Lowest surprise means better prediction.
Which means better understanding of the context, so our perplexity is better.
Got it. And the paper shows Mamba's perplexity just flattens out.
Yeah, pretty starkly in figure 2. After about 16,000 tokens, it sort of plateaus. It stops getting significantly better, stops extracting much new useful info from more context.
Even though there is more useful info there.
Exactly. Meanwhile, Transformers, despite that quadratic cost, do keep improving their understanding as they see more.
So Mamba hits the ceiling. Why? What's the underlying reason?
It comes down to that fundamental structure of RNN. They have to compress all the history, everything seen so far, into this fixed size hidden state.
Okay, so one little box has to hold everything from the start.
Pretty much. Think of trying to cram the entire Library of Congress into, like, a single notebook.
Not going to work.
Right, you eventually run out of space. You can't capture all the nuances, all the complex relationships across vast amounts of text if your summary space is fundamentally limited.
You're forced to forget things, basically.
Implicitly, yes. The compression becomes lossy, especially for subtle, long-range connections. It's a memory bottleneck baked into the architecture.
Okay, so that's the wall, the fixed hidden state. How did these researchers think about breaking through that? What was the aha moment?
The core insight, the real shift, was thinking, what if the hidden state wasn't fixed? What if it wasn't just a static summary?
Okay.
What if the hidden state itself could learn and adapt, continuously improve its own understanding as new information comes in?
Huh. So the summary itself gets smarter over time.
Exactly. Instead of cramming the library into a notebook, it's like the AI builds a custom dynamic mini library inside its hidden state, constantly updating and refining its structure based on what it's reading.
So it can keep learning where the old methods just ran out of space?
That's the idea. The hidden state becomes an active, evolving learner.
That feels like a fundamental change. So how do these TTT layers, test time training layers, actually do that? How do they solve this long context problem?
Okay, so the TTT layers make this happen. The hidden state is no longer static. It becomes a small machine learning model itself. It has its own weights that get adjusted.
A model within the model.
Kind of, yeah. The paper looks at two main ways to do this. TTT linear, which uses a simpler linear model for the hidden state,
Okay.
and TTT MLP, which uses a more complex two-layer neural network. More expressive power there.
Right. But the really wild part is the test time training.
That's the game changer. The learning doesn't just happen before you deploy the model. It happens continuously, even when the model is processing new, unseen data, what we usually call test time.
So as new words or tokens come in.
Exactly. As they arrive, the hidden state model is actively updated. It takes gradient steps, makes little adjustments to its weights.
Based on what? How does it know how to adjust?
Based on a self-supervised loss. It basically tries to predict aspects of the incoming data itself and uses its errors on that prediction task to update its own weights. It's learning from the data stream as it processes it.
Wow. Okay. So it's not just recalling facts, it's actively refining its understanding on the fly. I like your detective analogy earlier. The detective isn't just using old case files. As new clues arrive during the investigation, the test time, they're learning new patterns, making connections, updating their whole theory of the case.
Yeah, their internal hidden state is dynamic, adapting to the evidence stream. That's very much the spirit of TTT.
Makes a lot of sense. And the results. Does this actually work? Does it break that plateau we saw with Mamba?
It really seems to.
Yeah.
The performance results are quite promising. Both TTT Linear and TTT MLP, they don't plateau at 16K tokens like Mamba did in their experiments.
They keep improving.
They keep reducing perplexity, meaning they keep getting better at understanding the context as they condition on more tokens. They showed this up to at least 32,000 tokens on datasets like Books 3.
So significantly longer context than where Mamba stalled out.
Definitely. And compared to Mamba, even at, say, 8,000 tokens, both TTT versions perform significantly better.
And the gap gets wider at longer contexts.
Seems so. At 32K tokens, the advantage grew, especially for TTT MLP. The paper notes it shows larger potential in these really long contexts.
Suggesting that having that more complex, adaptable hidden state really pays off when there's more history to draw from.
Plausibly, yes. And crucially.
The efficiency question.
Right. They managed to do this while maintaining the linear computational scaling of RNNs.
No quadratic nightmare like Transformers.
Nope. You get the potential for deep, long context understanding without that exponential blowup in cost. It's aiming for the best of both worlds.
Okay, how? How do they keep it efficient with all this extra learning happening inside?
Good question. It ties into this learning-to-learn framework they describe. Think of it as two nested loops.
Okay,
The inner loop is that test time training we just discussed. The hidden state model, with its weights, W and EO, is constantly updating itself using that self-supervised task based on incoming tokens. It's learning what's important right now.
got it. Inner loop, immediate learning.
Then there's the outer loop. This happens during the main training phase, before deployment. The outer loop learns the parameters of that self-supervised task itself.
It learns the parameters of the task.
Yeah, things the paper calls LICA, TQ, LAKI. These parameters basically tell the inner loop how to learn effectively from the data stream. What kind of predictions should it make? How should it update itself?
Whoa, so the outer loop teaches the inner loop the best way to learn on the fly. The system learns how to learn.
Exactly. Table 2 in the paper lays out this nested structure. It's learning the strategy for adaptation.
That is pretty meta.
Yeah.
And very cool. But again, making this fast, all these loops and updates.
Right, requires some smart engineering. They use techniques like mini-batch TTT, updating the hidden state based on small batches of, say, 16 tokens at a time, not every single token.
Okay, batching helps.
But the really big speed-up came from a mathematical trick they called the dual form.
Dual form sounds intriguing.
It essentially reformulates the calculations needed for the updates. It avoids creating and storing huge intermediate matrices, which is often a bottleneck on modern hardware like TPUs.
So it optimizes the math for the chips?
Pretty much. It speeds up the training by more than 5x, according to the paper. This makes the whole TTT process much more practical.
That's crucial. It's not just a cool idea. They figured out how to make it actually run efficiently.
Yes. Bridging theory and practice.
And plus you mentioned these TTT layers aren't a whole new architecture, right? They can be added to existing ones.
Correct. They're designed to be plug and play, more or less. You could potentially drop a TTT layer into a transformer backbone or a Mamba backbone to enhance its ability to handle state or context. Makes them very versatile.
Nice. So it builds on existing work.
What's really fascinating, though, is how general this TTT idea might be.
How so?
The paper argues it's not just one specific mechanism, but a general framework. They show some really interesting theoretical connections. Well, TTT linear, the simpler one. Under certain settings, it actually becomes mathematically equivalent to linear attention, which is another known efficient RNN-like layer.
Okay, so it connects to other known techniques.
Even more surprisingly, they show that TTT, if you use a non-parametric learner in the hidden state, can actually replicate the behavior of self-attention.
Wait, the core mechanism of transformers.
Yes. This suggests TTT might be a more fundamental, unifying concept that encompasses both efficient RNN-style processing and the powerful attention mechanisms of transformers. It's like different ways of implementing this learning to learn at test time idea.
Wow, okay, that elevates it beyond just an RNN improvement. It's potentially a new lens on sequence modeling entirely.
That seems to be the implication, yeah. It opens up thinking about hidden states not just as memory stores, but as active computational units that learn and adapt.
So it's a powerful framework. But are there downsides? Current limitations, where does it stand now?
Definitely. It's still early days, and the researchers are upfront about the challenges. While TTT MLP, the more complex version, shows great potential on paper, it currently struggles a bit with practical speed, specifically memory input-output, moving data around.
So even if the raw computation, FLOPs, is efficient, the data shuffling slows it down in real-world clock time.
Exactly. Figure 12 shows this. It can be slower than, say, a highly optimized Mamba in practice right now, even if it's theoretically doing less raw math per step.
Okay, so a systems optimization challenge.
Precisely. It's not necessarily a fundamental flaw in the idea, but points to needed work in hardware-software co-design to make these dynamic hidden states really fly.
Makes sense. And the researchers acknowledge there's a huge space to explore here, right? Different kinds of hidden state models, different learning rules.
Oh yeah, a massive search space, as they call it. This is just the beginning for exploring these expressive hidden states.
So what kinds of future developments could stem from this? More complex hidden states?
For sure. You could imagine using convolutional networks inside the hidden state. For video, maybe, where spatial reasoning matters. Or exploring different optimizers for that inner loop, like Atom.
And tackling those memory bottlenecks.
Absolutely. Better systems optimization is key. They even mentioned multi-level learning to learn.
Learning how to learn how to learn.
Kind of. Imagine an AI that doesn't just learn from data, but refines its entire learning strategy over time. It's pretty mind-bending stuff.
Okay, so recapping this deep dive, TTT layers seem incredibly promising. They offer a way to keep the efficiency of RNN
Linear scaling.
while unlocking the kind of deep, long context understanding we previously only got from expensive transformers.
It's about AI that doesn't just get trained once, but continuously learns and adapts as new information flows in.
Which feels much more alive, more like how we learn.
That really gets to the core motivation, I think. Why go down this path? It's about building AI that learns more like humans do.
We don't get perfectly shuffled, independent data points.
No. We learn sequentially. We constantly adapt. There's no hard line between our training phase and our testing phase in life. We're always doing both.
Learning is continuous.
And TTT's inner loop, That constant updating based on new inputs mirrors that human process much more closely. It blurs that artificial train-test boundary.
It's aiming for a more natural, dynamic kind of intelligence.
I think so.
So here's a final thought for you, the listener. Imagine an AI that truly understands and processes information the way you do, constantly updating its internal model of the world with every new sentence, every report, every insight it encounters, learning on the fly, never really stopping.
Yeah, what new frontiers of intelligence, of understanding?
Yeah.
What could that unlock for all of us?
Something to chew on until our next deep dive.